Hey guys, how's it going? This is Siri, and in this video, we're going to be talking about tensor operations. Okay, so it's another PyTorch video. And now that we've talked about tensors, why we use them, we've talked about broadcasting, now let's talk about what we actually do with tensors, what we can do with tensors. And although when you're training a model, or you have a neural network, although you don't know exactly what's going on, you can, because behind the scenes you don't know what's going on, but you can get an idea and a feel for what may be happening, right? And you will know, right? Because you know what layers you're using. But you don't need to worry about that right now. Let's just see what kinds of operations we can do with multidimensional arrays, which are just tensors. Okay, so there are over 100 tensor operations, and these can be arithmetic, they can be linear algebra, they can be transposing and shifting matrix around. And so let's first talk about arithmetic operations. So this is where we operate on each of the different tensors, or each of the two tensors element-wise. So for example, if you had a tensor of 1, 2, 3, and a tensor of 4, 5, 6, the 1 and the 4, the 2 and the 5, and the 3 and the 6 would, they would add together or subtract, or whatever operation you're doing, and it would go element-wise. So every corresponding element should, get added or subtracted or multiplied or divided together by each other. Okay, so tensors of the same shape can be added, multiplied, etc. So this is the more intuitive thing. But if you want to talk about, tensors with different shapes, check out my video on broadcasting, because then you don't have this element-wise thing anymore, right? So we change up the tensors a bit so that we can do that, that element-wise arithmetic operations. Okay, so operations with the scalars are distributed over the tensors. So for example, if you have the tensor 1 equals torch dot 1s, so this is going to be shape 2, 3. So 2 rows, 3 columns. If you had more dimensions, you wouldn't really call them rows and columns anymore, because there are 6, 7, 8 dimensions. You don't have you can't visualize that in just our 3D space. But those tensors do exist. They're higher dimensional tensors, and you can have as many dimensions as you want. Okay, they're just lists within lists, or arrays within arrays. Okay, so okay, great. So now let's print out ones. Okay, we didn't import torch yet. Okay. Let's import torch, and yeah, we just get, see, 2 rows, 3 columns, which is just one overall tensor, right? 3 elements in each array. Okay, and there are 2 arrays. That's what this means here. Okay? So if you want 2s, what can you do? We can do the same thing, torch.1s, 2, 3. I mean, if you wanted different dimensions, if you wanted 4 columns, or 4 columns, or just 4 elements in each array, then you would put a 4 instead of a 3. If you wanted 6 rows, which just means 6 arrays, at least in the 2D sense here, right? Then you would do 6. You get the point, right? So now, how is this going to be equal to 2s? Right? This isn't 2s. This is just 1s. Well, if you multiply it by 2, you're going to get 2s. So you see here, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Okay? So another thing you can do, since these are the same shape, right? What you can do here is 1s plus 2's. Gets you 3's. Okay, so 1 plus 2 is 3. Okay, what a surprise. Okay, let's try this. Okay, so now we have 3's. You get 9's. 3 times 3 is 9. Okay, so yeah, that's the way it goes. And if you also wanted, I mean, you can see from here, but like if you wanted this dot shape, wanted the shape of this, you can really see that this is going element wise because it has the same shape, 2, 3. Okay? Okay, so let's see this. R1 plus R2. Okay, we didn't define R1 and R2 yet, but okay, torch.rand, which is just the same thing. R2 is equal to torch.rand, 2, 3. And these are different tensors, right? Because these are random. Okay, so we're going to be filling it with random numbers. I think from 0 to 1. Probably from -1 to 1 or something. Or it does change with n. Okay, so if you want to do R1, actually, wait, let's do this. 3, 2. So these are different shapes. Okay, so R1 plus R2. Okay, the size of a tensor, A, must match the size of the tensor B at a non-singleton dimension 1. Okay, so this can't even be broadcast together, right? Because when you look at the dimensions, you see 3 and 2, they're not the same, and one of them is not even 1. So you can't broadcast these together. And let's take a look here. If it was 1, oh, then this doesn't make sense, right? So maybe if this was 3, okay? 3 or 1 would work. So now it works, see? So if you're confused by this, take a look at my broadcasting video. I think it's explained nicely there. Like, you just take a look at the dimensions and you see, hey, is this, are these the same, or is one of them 1? Okay, if so, great. If not, then not great. Then you can't do broadcasting anymore. Okay, so 3, 2. This is not going to work out. Okay, so that's what I wanted to point out. So you can't do arithmetic operations with different sizes if they're not broadcastable. Okay, so yeah. So they need to be same sizes. A, they need to be same sizes, or B, they need to be tensors in which you can make them the same size. So essentially you can't do operations without being the same size, either now or like after conversion. Due to broadcasting. Okay, so let's take a look at a small sample of tensor operations. Okay, so let's say R is equal to torch.rand. And let's make it a 2 by 2 matrix, 2 by 2 matrix, and let's subtract 1, because the default actually is between 0 and 1, and after subtracting 1 from each element, it's going to be between -1 and 0. Okay. Okay, now it's between -1 and 0, and let's print out a random matrix R. Okay, let's print out R. This is something you should expect to see, right? So now the numbers are between -1 and 0, so they're all decimal values, and it's a 2 by 2 matrix. Okay, and that's our random matrix. Okay, so now let's print out a series of arithmetic operations. Okay, so first let's do some absolute value. Actually, wait, these aren't arithmetic operations, but like let's sample of tensor operations. Okay. in general, sample of tensor operations. Okay, so let's check out the absolute value. Absolute value of R. And you can do something like this, torch.abs, and then pass in the tensor in question, which is R. So let's also print out maybe the inverse sine or cosine. Okay. Arc sine, which is basically the inverse sine of R. So we can print torch.a sine of R. A is just arc, right? Arc sine, inverse sine, they mean the same thing. And if you're not familiar with these, just look them up, you'll be fine. Okay, so print maybe the determinant. So this is like a linear algebra sort of thing. Okay, so these all have to do with like matrices and stuff like that. So torch.det. Okay, print. Once again, this is another linear algebra thing. I mean, you don't need to know the ins and outs of linear algebra, but I would recommend getting just, familiar with the basics. Like, just look through an introduction. You don't need to look through the entire thing, but if you wanted to, and if you had time, that would be great, but I think going through an introduction would be good. Okay, so singular value decomposition of R. Okay, so print torch.s for singular, v and d, okay, of R. So yeah, let's only a few more. Let's check out some of the statistics and statistical sort of things. So maybe average and standard deviation of R. Okay, so average is just the mean, right? So you add up all the values and you, divide by the number of numbers there are, and standard deviation just tells you how much variation in the data you have. So, okay, like how spread apart are they? Okay, so let's do something else. Let's print the max and min. Maximum of R, print torch dot max of R. Okay, last one, let's just print the minimum, okay? Okay. So, we're gonna get a lot of stuff. Okay, so what did we do first? We asked for a random matrix of R, which is just our random matrix, 2 by 2 matrix, and we changed the range by subtracting 1. So now it's between -1 and 0. Remember, we can do this because it does this operation element-wise. So originally, every value in the tensor was between 0 and 1. Now that you subtract 1, every value gets subtracted by 1. And so now the overall tensor's range is -1 to 0. Okay, so that's a random tensor. The absolute value is the same thing, except, just positive. So it tells you the distance away from 0. The inverse sine Okay, determinant of R, singular value decomposition. Don't worry if this doesn't all make sense to you, but we get the average and standard deviation here, so we get two values, and the maximum and the minimum. And you see how these are tensors, right? Even for the single value ones, these are tensors. They're not just regular, Python numbers. But if you wanted to, so if you had a tensor just with one value, okay, this is only applicable to tensors with a single value. You could turn this into a Python number. So what you would do is take the tensor of question, so the tensor we're looking at, and we would do dot item. Okay, so for example, now we have, let's take the determinant. Okay, so let's set a variable equal to, the same thing, and let's just print dt. So there's no difference. We're just assigning this value to a variable. So now if you wanted to, okay, let's run this again. Okay, so if you wanted to take det.item, okay, maybe this doesn't show much, but you don't see the tensor anymore, right? The tensor and then parentheses this value. No, you don't. What you see instead is you see a float, a Python float. Okay, so yeah, this is a Python data type. Okay, so like for example, if you were to see type just a regular 7.8, you would get float as well. So this is Python float. And this only works for single value things, right? So for single valued tensors, use .item to turn it into a regular Python float, or int, depending on what you have. Okay. Okay, great. So another thing I wanted to talk about is in place operations. So these operations don't just, okay, so look here. Just to, okay. So now you see a type of dt. Print okay, so here the regular det is excuse me, is a tensor. So then what did we do here? We just returned a new tensor that had the value of det.item. Okay, we didn't actually change the value of det. So if you want to do that, then you would have to do an in-place operation, which actually modifies the tensor that you're talking about, and doesn't just return a new tensor with a certain modification. You want to change the tensor itself. Then you would do an in-place operation. And how would you do that? Well, you would use an underscore, okay, as part of it. So let me make this a bit more clear. But this is the suffix that you have. Okay. So for example, if you have print, like, what tensor did we look at first? Ones. We looked at ones, right? Yeah. Okay, we looked at ones. So print ones. Goodness. Okay. Print ones. Okay, so now print ones plus 5. Okay, 6. Print ones again. Still 1. Okay, there's another like function and we can say ones.add 5. Okay, that works too. So yeah, there are tons more on the PyTorch documentation. Check these out. These are factory methods. Okay, they help like initialize tensors, create tensors, and like modify them like this. Okay, so when you printed ones plus 5, you still get ones, right? You still get ones. Oh my goodness. Okay, still get ones. Okay, my point is that if you wanted to, do ones.add and then put this suffix at the end, and then do 5, and then print ones, the value of just regular ones, now you get 6. Okay? It's not just ones anymore. This is an in-place operation. Okay, in-place operation actually changes tensor, not just return. It doesn't just return value. It doesn't just return new tensor with modification. Okay, great. So now let's talk about, there's another operation which is, concatenating two tensors. So you can, put the tensors side by side, and this is really helpful if you want to clean up your data that you have. You might want to concatenate a few stuff, like concatenate, the different columns, the different rows, especially if you have non-tabular data. Okay, so let's take a look at how we join tensors. So you can use torch.cat for that, which is basically torch.concatenate. And we have T1 is equal to torch.cat, and we would do ones. We have twos too, right? So, and maybe they have to be the same shape along the dimension which you're concatenating it on, right? So for example, if you wanted to put the tensors side by side, then you would be concatenating along a certain dimension versus if you wanted to put them stacked on top of each other, right? So let's make another one called, actually let's redefine ones, because ones isn't ones anymore. We made it 6, right? So let's say ones, ones is that, twos is the same thing, except we multiply it by 2's times 2, and we do the same thing with 3's. Okay, except we multiply it by 3. We could have added 2 as well. So maybe T is equal to torch.cat, 1's, 2's, and 3's. Let's take a look. So dimension 1 would be like the columns, and dimension 0 would be the rows, right? That's always how it goes, rows first, then columns. So let's see, dim equals 1. Okay, so you see 1, 1, 1. You see this section of 1, right? You see my cursor, and you see 2, then you see 3. So we put it column-wise. We didn't do it stacked on top of each other. If we wanted to do that, then we would set dim, which is just dimension, equal to 0. And see, now they're stacked on top of each other. Okay, great. So I think that's basically, yeah, that's basically it. Yep, that's it. So there is one other operation that I want to talk about, but we'll talk about that after we talk about storage instances, because I think it'll make more sense, and it'll be more enriching if we do that first, which is just like, you know, transposing and doing other sorts of stuff with these matrices. Okay, so yeah, I think that's it for this video. Thank you so much. I hope you learned something about tensor operations, and I'm looking forward to seeing you in my next video. Don't forget to like, comment, and subscribe. Thank you so much.